Hi, in the previous episode we have seen how to generate sound that's received via the MIDI interface to the Arduino Mega. But we could only play one key at a time. Now we want to extend this to play two keys at a time and even more. So I've improved the code to handle multiple keys. But then this came up. I've realized that the data via the MIDI interface is received very slowly. And I wasn't sure what's the cause of this. You must know that the MIDI interface has a fixed bitrate of about 31 kilobits, so that should be enough. When you look closely at the Arduino, you can see that an LED is blinking whenever I press a note, and pressing much of them causes the errors. So my suggestion was that using RX0 interferes with the serial controller on the Arduino. So I wanted to shift it to RX1 or RX2. But there is where the problems are starting. This MIDI library that I have recommended in the last video is not working for other serial ports. They claim that it's working and there is some example code, but it doesn't compile at all. So I have tried for many hours and searching for solutions, but I couldn't find any. So I've just decided to replace it by my own code. This is so annoying. Every time you try something uncommon with the Arduino, it just fails and you have to go down to the low-level stuff. The MIDI interface is now connected to RX1. I have also replaced the 10K resistor by 560 ohms. It has a much better rise time for the signal. You have to try what's working best for you. It works much better now. As you can see, the delay is almost gone, but it's not perfect. I'm still using the serial object from the Arduino API. I'm thinking about to replace it as well, but this may be in another video. Let's check out a bit more complicated code now, and also how this compression works that allows us to add multiple sounds with less distortion. I have removed the MIDI library now. And additionally we have another table here, that's the compression lookup table. It has 4K values. I will get to this later. Then we have a new class that's called note. Each note that is playing is handling themselves, so it has own parameters. We have the velocity, the frequency increment and the phase, like before, and additionally we have a state for this note, so this can be playing or just stopped, and we also saving the key number. The constructor just sets the state to -1, which means that the note isn't playing at the moment. Then we have note on. It's setting the state to -1. If the note is already playing, then it's just muted as long we set the values here, and at the end it just started with state equals 0, and in between we just save the parameters here and look up the frequency table. Note off is simple, it just sets the state to -1. Then we have the mix function. The mix function returns the current sample for this note. So first of all we take the sample, which is for the sawtooth just the upper 8 bits of the phase, and we shift this to be balanced around 0, so it has negative to positive. Then we multiply it by the velocity, and since the velocity is just 7 bits, we shift this again back 7 bits and increment the phase by the frequency increment. That's done for each note that's playing. The MIDI interface can handle 16 channels and 128 keys per channel. So we want to save some kind of a state for each of these keys. And then we want to play up to 16 notes here at a time. So we have an array of up to 16 notes. And this note map here stores just an index to this array here. So if the note is playing for a certain key, an index is stored which points to the note here. If the key is not playing at the moment, there's stored a -1. We still have the node off and the node on functions here, but they have changed heavily. Let's get to node on first. I mentioned the case that when node on with velocity 0 is played, that's another case of node off. So we check if velocity is 0, and if it is, then we just call node off and return afterwards. If it's a node on, we just check if the index is equal or higher to 0. If it is, then the node is playing. So we just have to restart the node by calling on again with the new velocity. If it's a new node that's not playing at the moment, we have to find a free spot in this node array to fill in the values. So we just go through the complete array of the nodes and check if the state is -1. If it is, then we can fill the spot. We just have to write the index to the node map and then just start the node and break the for loop since we found the spot here. The setup has changed a bit. We are not initializing the MIDI library here, just initializing the serial 1 with 31250 bits per second. That's the common rate for MIDI interface. Additionally, we are setting this map to -1 for each value, and that's all for the setup. In the timer interrupt, we have now to check the array of nodes and check if the node is currently playing, and if it is, we have to add up the sample that we get from the mix function here. This can add up to 16 values from -128 to 127, and we have to cover this range by this table. So the table is just shifted by 2048, which is the minimum value that we can get from the samples here. But what does this compression table contain? You can read much information about dynamic range compression from this Wikipedia article here. But let me explain in a short what we want to do. So let's see this picture here. What we have done so far is a hard clip. So we have this range here that we accept, and we just set to the minimum and maximum values here. The problem about the hard clip is that even something changes up there, we can't hear anything. It's just a complete silence during it's over the range and below the range. So our solution can be only some kind of soft clipping. In a short, whenever something changes up there, it also should change something here, but in a lower extent. So we have less distortion and we can hear any changes, even it's too loud. But what kind of function can we use to achieve this? The most basic one is the Arcos tangents. The Arcos tangents is asymptotic to half of pi. So it's linear around 0 and then just getting closer and closer to half of pi, but never reaching it. And that's what we want. No matter how high our input is, it will never exceed our limits, but it's still a smooth function. So this is the function that I have used. First of all, I use a factor inside of Arcos tangents to get the slope that I want to have. Then I divide by half of pi and multiply by my accepted range. This should be 128, but whenever I use this, it will not just use the complete range. So this is my value, you have just to play around. What I have done additionally is to shift the result by 128 up to end up in the positive range that we can output directly to our port. So we can just add up 128 here. Let's do a direct comparison. First, the hard clip with playing 3 notes on maximum velocity. You can clearly see the limits where it's clipped. Now the Arcos tangents with the same notes and same velocity. The curve is smooth and asymptotic to the limits. No information is lost and the distortion is lower. Let's get back to the code. So at the end you have just to know that it works. Since we have removed the MIDI library, the loop is a bit more complicated now. We have to handle each byte of the messages and just take the message that we want to interpret. I have 2 globals, the count that saves the bytes of the comment that we have stored and an array for the 2 first bytes that we have stored for the comment. We repeat the code as long as we have still some bytes in our buffer. We get the byte and then check if it's a start of a comment. A MIDI comment starts whenever the highest bit is set. So if a byte is above 127, it means a comment starts. sysx comments are an exception, but we will ignore this for now. So we detected the start of a comment and we set the counter to 0. Afterwards, if the count of bytes is below 2, we just store the byte in the array here and increment the counter. If it's not the start of a comment, we just check if we have already stored 2 bytes, since the comments that we are interested in have 3 bytes. The upper 4 bits of the first byte of a comment indicates the comment type, and the lower 4 bits indicate the channel. So we check if it's a note on, and then write the channel, the note, which was stored as well, and the newest byte, which is the velocity. If it's a note off, we do the same, just with the note off function here. And that's all for now. We can program it and check if the polyphonics are working. Sounds promising. That's enough for today. In the next part we will handle the adsr envelopes. I hope this is a bit more interesting. So subscribe and tune in again. Bye.